Welcome to the new session on real analysis. So far, we were discussing the problems and theorems on real numbers and its properties. In this session, we will be discussing the new properties or the properties of a new term called real functions. So, real functions are the functions which are defined on a subset of real numbers, and the range is also a subset of real numbers. So, among the properties of the functions of real numbers, the first and foremost that we have to discuss in detail is the concept of limits. So, the concept of limits is like this: let A be a subset of R and C be a cluster point of A. So, a cluster point of A means it is a real number to which every point of A is coming close to. If f is a function from A to R is a real number L is called the limit of a function f if given epsilon greater than 0, where epsilon is a very small number between 0 and 1, there exists another real number delta greater than 0 such that whenever x is an element of A and x is in the delta neighborhood of C, that means 0 less than modulus of x minus c less than delta, it indicates that modulus of f of x minus L is less than epsilon. So, let us see a geometrical approach of this concept, namely we are given a subset of R and f is a function from A to R with x belonging to some delta neighborhood of C. So, modulus of 0 less than modulus of x minus c less than delta implies minus delta is less than x minus c less than delta, or we have x belonging to open interval c minus delta c plus delta. So, whenever we have x belonging to c minus delta c plus delta, this implies modulus of f of x minus L is less than epsilon. So, that means f of x becomes an element in the epsilon neighborhood of this real number L. Then we will say that L is the limit of the function f. So, let us see a geometrical approach. So, this should indicate that f of x lies in the epsilon neighborhood of L. That means it should be something like this: L minus epsilon, L plus epsilon. So, how we can see the geometrical approach is like this: if we have the x axis and the y axis, always we plot x on the x axis. So, we have c minus delta, c plus delta as the open interval here. We have the function f something going like this. We do not know whether it is a function with no breaks or function like this or something. It is a random function given. So, whenever x belongs to this interval, your f of x should lie between L plus epsilon and L minus epsilon. So, somewhere here your f of x should lie. Whenever x belongs to this interval, f of x should be somewhere here. So, f of x should be somewhere between L minus epsilon and L plus epsilon. So, whenever this happens, we say that f of x is very close to L as x becomes closer and closer to C. Then we will say that this function f has limit L as x approaches C. So, we can express this entire discussion as limit x approaching C f of x is equal to L. So, this is the notation used for representing whatever we have expressed or discussed so far. So, as an example we can see, suppose you have a function say f from R to R itself, defined as, say, f of x is equal to x square, and we want to find limit x approaching to f of x, how will we do this? So, given f of x is equal to x square, we want to find limit x approaching to x square. So, this is what? That is the question. So, using the diagrammatic approach that we have just now seen, we know that f of x is equal to x square is a parabolic shaped figure. It is a well-known shape or well-known function. It is a U-shaped parabola. Somewhere here you have your 2, x is equal to 2. So, we take this interval 2 plus delta, 2 minus delta, and look at the graph of the function f of x is equal to x square and see in which interval does this belong to. So, when you apply the value 2 minus delta to the function, f of 2 minus delta will be equal to 2 minus delta the whole square, which is equal to 4 minus 4 delta plus delta square, and when you put f of 2 plus delta, this will be equal to 4 plus 4 delta plus delta square. So, remember this delta and epsilon are very small positive real numbers. It is like 0.1 or 0.5 or 0.05. Between 0 and 1 we are placing this delta and epsilon. So, these two values are very close to which real number? These two are very close to the number 4. So, 4 minus 4 delta plus delta square is on this side, and we have 4 plus 4 delta plus delta square as this value. So, as delta approaches 0, x becomes equal to 2. So, when delta becomes 0, this interval becomes very close to 2, or it becomes exactly equal to the number 2, and here when you put delta equal to 0, these two image values becomes close to 4. So, that is the geometrical approach of getting the limit, and we have limit x tends to 2, f of x is equal to limit x tends to 2, here f of x is x square, and that is exactly equal to 4. So, this is how we get the limit using a geometrical approach, and that is exactly expressed in this representation using delta and epsilon. So, this is the concept of limit. Okay. Now, the limit of a function, if it exists, is unique. That means no function can have two limit points or limit values corresponding to x tends to x is equal to some value c. So, this is again proved like this using the epsilon delta definition that we have noticed. Proof: if possible, let limit x approaching c, f of x is equal to say L1, name it as equation number 1, and we have limit x approaching c, f of x is equal to L2, name it as equation number 2. So, we are supposing we have to prove that if for a function f, if it has a limit, it has to be unique. So, if possible, we are assuming that the function has two limits as x approaches c, namely L1 and L2. So, also we will suppose that L1 is not equal to L2. Okay. So, what we are going to prove is this cannot hold, this is wrong. We have to show that to prove that L1 is equal to L2. This is what we are intending to prove. So, by using the definition that we have seen in the slide, 0 less than modulus of x minus c less than delta, I will write delta 1 because we have assumed the function has two limits, indicates that or implies modulus of f of x minus L1 is less than epsilon, given epsilon greater than 0. Also we have, so there exists a delta 1 greater than 0 such that I am not writing the full details. Also given epsilon greater than 0, there exists a delta 2 greater than 0 such that 0 less than modulus of x minus c less than delta 2 implies modulus of f of x minus L2 is less than epsilon. So we can write say epsilon by 2 also here, so that we will require it later. Name this as inequality number 3, inequality number 4, because 1 and 2 are already used there. So using these two we can have consider delta equal to the minimum of delta 1 and delta 2, so that why choosing delta to be minimum? Because whenever 0 less than modulus of x minus c less than delta, this will imply 0 less than modulus of x minus c less than delta 1 and 0 less than modulus of x minus c less than delta 2. That is why we are choosing delta to be the minimum of delta 1 and delta 2. So whenever this holds, automatically 3 and 4 holds simultaneously. Therefore, consider modulus of L1 minus L2. Then we can insert f of x in between, modulus of L1 minus f of x plus f of x minus L2, which gives you modulus of L1 minus f of x plus this we can take as one term plus f of x minus L2 becomes the other term. We are going to apply the well known result of triangle inequality. So this is less than modulus of f of x minus L1 plus modulus of f of x minus L2, and this is less than epsilon by 2 plus epsilon by 2, and hence this becomes less than epsilon. Therefore we have 0 less than modulus of L1 minus L2 less than epsilon for every epsilon greater than 0, because we had started with an arbitrary epsilon. So remember, in real analysis, in most of the proofs we will be applying the same techniques. So in previous cases also we had applied the same technique, and if you remember, we had studied a result 0 less than a less than epsilon for every epsilon greater than 0 pushes your a to be exactly equal to 0. Okay. So using this result, we have your L1 minus L2 is approaching equal to 0, which indicates that L1 is equal to L2. So that shows that if the limit of the function exists, it should be unique. Okay. Now the next important result that we have in this limit is, if A is a subset of R and f is a function from A to R which has a limit at C belonging to R, then f is bounded on some neighborhood of C. So this is also analogous to a previous result that we have discussed in sequences chapter for convergence implies boundedness. So the proof is a similar one. So we are going to show that if limit x approaching C f of x is equal to L, this should imply f is bounded. Now there comes a question, when do we say that a function is bounded? So a function is bounded if the range set is bounded. That means if the images are bounded, we will say the function is bounded. So first we will discuss what is boundedness of a function. F is bounded if there exists some real number m such that modulus of f of x is less than or equal to that real number capital M for every x belonging to the domain. So, here I am assuming f is a function from a to r. So, modulus of f of x is less than or equal to m for every x belonging to a. We will say that the function f is bounded if we are able to find such an m. So, for example, we can find sin x is bounded because modulus of sin x is always less than or equal to 1. Likewise, cos x is bounded. So, we have this boundedness theorem like this. If limit exists, f is bounded. So, that is the theorem saying. This is just a definition for boundedness. Now, coming to the result proof of the theorem. We are given that limit x approaching c f of x is equal to L. So, given epsilon greater than 0, there exists a delta greater than 0 such that modulus of x minus c less than delta implies modulus of f of x minus L is less than epsilon. In particular, for convenience of proof of this theorem, we are assuming epsilon equal to 1. So, when epsilon equal to 1, we have modulus of x minus c less than delta implies modulus of f of x minus L is less than 1. Now, we have already studied a result, modulus of mod a minus mod b is less than modulus of a minus b is less than epsilon, indicates that we have the result modulus of f of x minus L is less than 1, and so using this result we can have modulus of f of x minus modulus of L is less than 1. We can omit this modulus sign here. Modulus of a minus modulus of b is less than mod a minus b, which is less than epsilon. So, from using this result, using this result we can have, we will have modulus of f of x minus modulus of L is less than 1 whenever modulus of x minus c is less than delta. I am omitting 0 less than because obviously modulus sign whenever it comes it is greater than 0. So, modulus of f of x becomes less than 1 plus modulus of L whenever x belongs to this delta neighborhood. So, we can have some capital M is equal to supremum of modulus of f of c and 1 plus modulus of L, and this M will act as an upper bound for f of x, so that f of x is less than or equal to M for every x belonging to c minus delta, c plus delta, because the limiting case is applicable for x not equal to c, and since we have taken supremum of modulus of f of c and then 1 plus mod L, so this is applicable for every x belonging to this open interval. So, that completes the proof of this result. Now, these are the algebra of limits. That means, if you have sum of functions, difference of functions, product of function, constant multiple of function and so on, correspondingly what happens to the limits. So, if A is a subset of R and f and g are two functions from A to R such that they have the limits L and M, limit x approaching c f plus g is equal to L plus M, limit x tends to c f minus g becomes equal to the difference of the limits, product function goes to the product of the limits, and constant multiple has constant multiple of the limit. So, the proofs are quite simple. We can apply the triangle inequality for the proof of this, and the proof of this becomes a bit more conditions required, like boundedness condition is also applied. This is also followed from directly by the properties of real functions, that real numbers that we have learned. Lastly, we have, if f and g are two functions having limits L and m, provided g of x is not equal to 0 for every x belonging to the domain and m is not equal to 0, we can have limit x approaching c, f by g is equal to L by m. So, this is called the quotient rule for limits. So, here additionally one condition is required, that the denominator should not be equal to 0. Next limit theorem is called the sandwich theorem or called the squeeze theorem, where we have three functions f, g and h such that the function g of x is sandwiched or squeezed between g of x and h of x, and if both the functions on the two ends are going to the same limit as x approaches c, the intermittent function or the middle function has no other option, it also has the same limit L. So, this is called the sandwich theorem or the squeeze theorem. So, it also can be expressed using a geometrical picture, and we can see that the limit also goes to L, or there can be a proof for this using this condition, and we have the condition given for limits. We have modulus of f of x minus L less than epsilon for modulus of x minus c less than delta, modulus of h of x minus L less than epsilon, and so modulus of g of x minus L also becomes less than epsilon. So, these are some of the theorems on limits and the concept of limits that we have discussed so far. So, this is the regarding the limits of the functions. Thank you.